Okay, let's look at an example here. This may not have ever seen this one before, but this is the greatest integer function. And it looks kind of like this. Wait, that symbol, I don't know if I have that symbol, but okay, so this one in here, greatest integer function. To generate the graph, we're going to just look at a few points here. Oops. Back to that. Okay. There it is. Okay. Let's generate a few points here. Okay, so let's start with, let's start with 0. What's the greatest integer less than or equal to 0? Well, we always try to go bigger than 0 if we can, but we can't because the greatest integer less than or equal is actually 0. Okay, greatest integer, let's go to 1/2 for x. The greatest integer less than or equal to 1/2, we'd like to go to 1, but we can't because that's bigger than 1/2, so it would have to also be 0. And likewise at a 3/4, same thing, greatest integer less than or equal to 3/4, it's got to be the 0. So that happens all the way until you get to 1. And right at 1, you get to put in a 1 then, because the greatest integer less than or equal to 1 is a 1. And then, of course, when you go, you continue, 1.2 is still 1, 1.3 is still 1, and so on, all the way up to 1.99999, still 1. When you hit 2, it jumps to 2. So graphically, what you're looking at is, so far we have a point here, we come all the way over to 1, and then it jumps up. So there's a hole here, and this one continues this way, another hole jumps up to 2. Oops, I don't like that. It disappeared on me. Jumps up to 2, continues, and it continues in that fashion up this way like a set of steps. So you got each of these, a dot on one side and a hole on the other. Okay, and it goes backwards this way too. We could put some negative values in if we wanted. Okay, I wish I knew why it was disappearing like that. Okay, so this continues on left and right, so forth. Now, we're actually trying to find the limit as x approaches 1 from above. So we come over here and we're approaching 1 from above, so we have to be along this path in here. So you're gonna be coming down this route right in here, the red, and you're heading to this point right here. Because x is bigger than 1, so you're coming in here for x values, and you're coming along this line until you reach that point. So remember, we don't actually have to reach the 1, but we can see that the values for the function are staying at 1, and they will stay at 1 as close as you want to get to x equals 1 here. So our answer is just 1. You can see that from the graph. It's 1 high, basically. So, okay, now let's continue. You can also see that in the table that we built, coming along this direction here. You're coming along here, getting closer to the 1 in here. X is bigger than 1, heading to 1. Notice the y values are always 1, and they stay at 1. Okay, so this is a right-hand limit. Now notice the left limit, although don't ask for it in this problem. If you were trying to find it, it helps to look at this one together. with the other one. This time you'd be coming from the other direction. You'd be down here, approaching x equals 1 along this path. And here you can see the height is always 0. And it will be 0 all the way till it gets to that hole. It's still 0. So this actually would be a 0. And you can see how the two-sided limit then would not exist. Okay, if you were trying to calculate this, this would not exist. Because the left side, this one, does not equal the right. When we calculated those two one-sided limits, they're not the same. So they're not the same, therefore the two-sided limit does not exist. All right, so that was a lot there. And here's kind of a summary of what I was just saying regarding that. So just here, that's the two-sided limit. It's only going to exist if the limit from the left, or the left side limit, and the limit from the right are the same. They have to exist, and they have to be equal. Both have to exist, and both have to be equal. So, if and only if. So, everything has to be perfect for this. Both of these must exist, otherwise this one does not. Okay. Okay, here's our definition of continuity on a closed interval. It would be, it's a lot like continuity on the open, except it requires continuity on the open. And then these limits from the left and the right, limit from the right as you approach x equals a, and then limit from the left, they have to be equal, exist, and they have to be equal to the function value at a and b also. So the limit has to exist, and it has to be equal to the function value at b and over here at a. So we would say that function is continuous from the left and from the right for those functions. Okay, here's another question about domain. This is just maybe a little review of your college algebra topics, but the domain is any value of x that generates a meaningful number for our expression. And you can see that's only going to happen if this thing is greater than or equal to 0. Now you could treat this as a quadratic inequality, or you could just say, you know what, I know that looks like a function I'm familiar with. That function is a parabola. It kind of looks like this. It's upside down, like that, 2 and negative 2. Up here at 4. Okay, it's 4 high, 1, 2, 3, 4, and it's 2 over, 2 left. Okay, so where is this thing greater than or equal to 0? Only between negative 2 and 2. Therefore, that's the only place I'm going to have a square root of a positive or non-negative number, right between negative 2 and 2. So, what's the domain? Has to be negative 2 to 2. Because that's the only place that this expression, as we can see from the graph, would be positive. It's positive because it's above the x-axis. Okay, so that's graphically how we could settle that. Okay, so now this, I said this was equal to y here. Okay, I was just analyzing the inside of this function here, this composition. Okay, so I looked at just this, which is a parabola. But now the function itself is not a parabola. I was just using this to analyze it. Function itself is actually a semicircle. basically it looks like this. -2 to 2. Okay, but I was looking at the inside in here. All right, discuss the continuity at the interval boundaries. Well, this is continuous, and to use our new vocabulary, go back up here. It's continuous on that closed interval. Okay, it's continuous from the right at -2, and continuous from the left at +2, and it's continuous everywhere between -2 and 2. So it is continuous on this entire closed interval. Okay. So that's using the terminology. All right, where is this function continuous? Well, gotta know a little bit about the cotangent. Best way to look at the cotangent, if you don't have it memorized, is just to think of it as the cosine of x over the sine of x. And then you can say, well, this will have to be non-zero for this to exist. So we can pick off discontinuities wherever this denominator becomes 0, because that would, and as long as the numerator is not simultaneously 0. But we know the sine and cosine don't have the same zeros, so that's not going to be a problem. So all you have to do is answer this question. When is that 0? Well, you know that's 0 at odd multiples, so you could say 2n plus 1 of pi over 2. Or this is a good way to say it, n is an integer. Okay. Or you could just spell it out in words, and say odd multiples of pi over 2. So, you know, I can take that back. What is it, 0? It's 0. Okay, you have to pardon me for that. I'm going to go backwards here. What was I thinking when I said that? Let's see. 0, or not. This is when it's equal to plus or minus 1. I don't want that. I'm going to take it back. I apologize for that. Hope you didn't get scared when you heard that. Some of you might have been thinking, wait a minute, what's he talking about? Okay, so I'm back here. X, this would be 0 at n pi, where n is an integer. Okay. Anytime we have n pi, n being an integer, will equal 0. So at x equals 0, at x equals pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. And in the negative places also. So we have discontinuities there. So on what interval is it continuous? Well, rather than list a whole series of intervals here, a union of intervals, we'll just say that continuous only for x not equal to n pi and an integer. Okay, that's a good way to say it. Otherwise, we would have to use a long-winded statement in interval notation. So, because it says on what interval is this continuous? So you'd have to put together that whole string of intervals, throwing out these asymptotes. These would be asymptotes at n pi. So continuous only for x not equal to these numbers. And that would mean you'd have to, we're not even going to write it like that. It's just too inefficient to use an actual interval. Rather easier to just list the discontinuities. Okay, what kind of discontinuity does this have? Is it removable or non-removable? Okay, well, first of all, let's locate the discontinuity. You can see you're going to have a problem if this occurs. because it means the denominator is a 0. Okay, regardless of what happens in the numerator, this function is undefined whenever that denominator is 0. Now, is it a removable undefinedness or not? That's the question. But this is going to be undefined regardless whether it's removable or not. So this is your first step. Find where is it 0 and therefore undefined. Okay, and that where it's undefined will give you a discontinuity. We'll figure out which kind in a minute. But okay, so you have this equation. Oops, that's x there. And that means squaring, you'll have x equal 4. Okay, so when x is 4, we have a discontinuity. Okay, now what is it? Well, to look at what it is, you'll have to try to figure out a better way to write this, because it might be a hole. In other words, when you look at that limit, let's just take a quick look at the limit. X goes to 4 for this. You notice you're going to get a 0 over 0. So when you notice that's happening, you're thinking potentially you might have a hole. Okay, if only the denominator is 0 and the numerator is not 0 at that number, then you have an asymptote, and that's non-removable. So you can say that again, if the denominator is 0 and the numerator is not, then it's an asymptote. But at 4, you can see that they're actually both 0. So now the question is it a hole? It might still be an asymptote, but let's see what happens. If we can get that division by 0 to disappear through a cancellation, if that can happen, then we know it's a hole. So what you'll do for this one, we've seen these before, there's a couple ways to handle them. If you take your expression, you can think of this as a difference of two squares. Square root of x squared minus 2 squared. And then that allows you to write it as a factorization of the difference of two squares, which is just root x minus 2 and a root x plus 2 over the root x minus 2. And you'll see that cancellation. So really, the function agrees with this one. Our original function agrees with this new function at all but one point. So now, if you look at what happens at 4, remember, you're finding this limit over here. It's now equal to this, whatever this is. Well, that looks like it's actually a 4, isn't it? So that does tell us that because this canceled, we know this tells us that we have a hole, since the denominator can no longer be 0 now at x equals 4. So it is a hole. Holes are removable. Okay, holes are removable. All right, so we do have a removable discontinuity there, and it is what's known as a hole. Okay, so let's do, I think, one more thing to do here. Okay, intermediate value theorem. Now, this one's important for, more theoretically important for proving things that very basic concepts, but important nevertheless. If f of x is continuous on the closed interval and f of a not equal f of b, and k is any number between f of a and f of b, between means not necessarily equal to, although technically could be. Could be a constant function, but if k is any number between, then there's at least one number, c, on this interval, such that f of c equals k. Okay, so, and as it said here, notice it plays an important part in proofs throughout calculus. It settles questions and is useful in different places. Okay, so now graphically what this is saying is this. Let's look at it graphically, the theorem. You have a continuous function from A to B. Okay, it's a closed interval. So the function exists here. Let's say f of A is here. And it can't be equal to f of B, so f of B might be over here. Okay, notice it's lower than f of A. Okay, now f is continuous, so that means I can draw a curve going from f of A to f of B without lifting my pencil off the paper. So I might do this. Like that. Okay, now, next condition is that if k is a number between f of A and f of B, then there is a c down here, somewhere between A and B. There's a c such that f of c equals k. So if you pick a number in here, okay, here's f of A, f of B is down here, and in the middle you have k. So what this says is that somewhere in here, there's one place, boom, you got a c. There's actually another place over here, another c. So this could be C1, C2, and here's another one over here. If you continue over, boom, you got another one, C3. The theorem says it's guaranteed to be at least one number. Okay, so at least one number. So now, k is any number between f of A and f of B, so it might actually be f of A or f of B. So it is possible. So if that happens, like for instance, you might have a case like this. Here's f of A, and here's f of B. And let's say k is up here. It is equal to f of A. Okay, let's draw this. There's A, and here's B. And all that's required is that I have to get down over here to B. It's continuous. It could go up and down or whatever, but it has to at least do this. It has to come over and touch over here at f of B. So what this is saying is that turns out, in this case, if k is right here at f of A, then there is one value. It's right at C. C would actually be equal to the A. But that's guaranteed by the theorem. C is in here somewhere. So that's one. Okay, so let's verify that this happens down here. Verify that IVT applies and then find the value of C guaranteed by the theorem. So here's the interval, here's the A and the B. And this is the 0 is equal to the K in our problem. So let's calculate f of 0. And that's an 8. Let's calculate f of 3. That's 9 minus 18 plus 8, which is a negative 1. Okay, so we do have our first condition met. And we are working with a continuous function. This is a polynomial, it's continuous. And we do have the second condition met, that we have f of A not equal to f of B. Now, our third condition is that k has to be between f of A and f of B. So k is 0. Well, there's a 0 between negative 1 and 8. Okay, 0 is between there. So all three conditions are met. We have continuity, we have f of A not equal to f of B, and we have k, a number between 8 and negative 1. And it could actually be the 8 or the negative 1, but in this case it's 0. So everything fits. That means the theorem tells us that there must be some number inside there between those two where we get a 0. In other words, k equals 0. We use this idea when finding roots all the time in back in college algebra and polynomial root theory. If the function changed its sign, in this case, notice one's positive, one's negative, it must be 0 somewhere in between, and we would search for that value. Then, knowing there's a 0, we would narrow down our search for the root to be between 8 and -1. Somewhere in there, we know there's at least one root. Anyway, this will find it for us. Now we're going to calculate that c right now. So you might say c squared minus 6c plus 8 equals 0. This does factor, so we have a c minus 4 and a c plus 2. So c equals 4 and c equals -2. Now, it guaranteed there was at least one. We got the 1 here. This is the one that was guaranteed. Okay. Now, it happens to be another one, but it's not between our A and B. That's okay. It's still there, but this is the one that was guaranteed by the IVT. So don't worry about this other one here. The theorem did not say that we couldn't have other zeros. It just said that we're guaranteed to find one of them between there's the 0 and the 3. Let's see, it's 4, -2, 4. I'm sorry, there's a -2 here. Sorry about that. That's a 2. Okay, so this is not the one. It's not the 4 that's guaranteed. It's the 2. Sorry about that. I was thinking when I wrote that. Guaranteed, this is the one. It's the 2. The 4 is the extra one. Okay, I mean, it's meaningful, but not to us here. 4 is the extra one. It's not between 0 and 3. But the theorem never said that that couldn't happen. It just said that you're going to get one of them, at least one, between 0 and 3. And this is the one that we found, the 2. Sorry about that. Okay. Factoring error there. Okay. So that's enough for now.